Hello everyone. Let's begin this mind map for the chapter which is work, energy and power. First of all, we will discuss about each of the terms, but first coming to the energy part. What is energy? Energy is defined as the capacity of an object to do work. For example, let's say there is this person. How do you tell that this person is energetic? You will call this person energetic only if maybe it is running around, or if it is able to lift up some object and maybe keep it aside or do some sort of work. If only if the person is able to do some work or do some movements, only then you call that thing as having energy. So energy is the capacity to do work, capacity to do some work. Work means anything, uh, maybe moving an object from this place to that place, or maybe stopping a car, things like that. So that is the capacity of an object to do some, or provide its capacity to do some sort of work in the process of these type of work. For example, there are different types of work. We will define work as well. What is work is, see, these work and energy are very much related, because one cannot be actually defined without the help of each other. That's the thing with work energy and energy. The work is defined as, let's say, you have an object, a heavy object, and maybe some friction is also acting here. It is a friction floor, or maybe there is this object that is there with some mass m, and you want to lift the object upwards in the presence of gravity. Then what you'll have to do is maybe work on the system, pull the object upwards. It means you must be imparting some of your energy inside it, right? So that's the thing that came up. While defining work, we are taking the help of energy, and while defining energy, we inherently depend on work. So these are like, actually these are the same things which go hand in hand. So what I was telling is, if you want to pull the object upwards, you will have to put some energy, some of your energy into the system, so as to pull the object upwards. And in the process, if any other person is there, that person will say that you have done some work over here. You have probably done some work, or whoever has hired you to do that work, maybe they'll pay you anyway. So that was work and energy. Now we will try to find out, or try to see, there may be different types of energy. First of all, what's the energy? Energy is the capacity of an object to do some sort of work. Now, the energy can be in many forms. It can be mechanical. Mechanical means an object having maybe some velocity in either direction, or any of the directions. Then that actually this specific type of energy is called kinetic energy. The term kinetic itself says it is all about motion, right? Kinetic means motion. So energy associated with with the motion is called kinetic energy. That is a part of mechanical energy, kinetic energy. And there may be another part which is potential energy. Potential means this particular type of energy has the potential to do some work, has the potential to do some work due to its the virtue of its position. For example, if this object is here, it may be having a possibility to do a work of maybe 20 joule. And if the object is here, then it may be having a possibility of doing a work of 10 joule. So depending on the position of the body, if the potential of the body to do some work changes, that type of energy is called potential energy. All right. There may be another type, which may be chemical energy, that you might have learned in your chemistry classes. For example, these are the two atoms which are bonded with each other. Maybe this is hydrogen atom and this is the hydrogen molecule overall. This is bonded between each other, and if you dissociate this chemical bond, you'll get maybe some enthalpy. What do we call it? Yes, enthalpy. Enthalpy is in the form of heat, right? Heat. So what is heat? Heat is nothing but a form of energy. So it means that this bond that was in between the hydrogen atoms also has some sort of energy associated with it, right? That type of energy is called chemical energy. Chemical energy. The third type may be called as nuclear energy. Some might say that nuclear energy is a part of chemical energy, but it is slightly different here. The nuclear energy is actually because of splitting of nuclei or fusion of two nuclei into one. We'll look into it, the equations related with it. The other type of energy may be mechanical, chemical, nuclear, maybe heat energy itself. All right. Another maybe electrical energy. So I think there are many dimensions. The electrical energy is nothing but some sort of chemical energy itself, because in the electrical energy, or you can even define it in terms of mechanical energy or the kinetic energy of the electrons. So electrical energy is nothing but the flow of current, right? Or the flow of electrons. If electron is flowing in this direction, the current will be flowing in that direction. But either way, it doesn't matter, because it has some energy associated with it, right? Electrons. And that form of energy is called as electrical energy, although it may be kept as maybe kinetic energy itself also. So what we'll do is, in each type of energy, we will try to maybe uh, quantify them. All right. So first of all, coming to mechanical energy, there may be a few types here. First of all, the first type, straightforward, is kinetic energy. All right. How do we get kinetic energy? The formula is very clear for that, half mv square. But how does it come up? I'll tell you how it comes up. See, uh, first of all, I think maybe we can discuss the work done part first, so that it's very easy to determine other forms of energy. All right, because I'll have to take the help of work to derive the equation for kinetic energy. That's why we are taking up the work part first. Now, what is work here? Work is said to be, let's say, there is this object and it is here. All right. Now, when you pull this object upwards with some force F, um, and let's say there's this gravity acting on it, what do you think? If the body moves up, it means your force is greater than the acceleration, or it is at least equal to the acceleration due to gravity, due to which the body is moving up. So, whatever work you're doing, try to understand it in layman terms. The work that you're doing must be directly proportional to the force. The more the force you're using to pull the body, the more that you are getting exhausted. It means the more you are, it means more you are doing work on the system. All right. Now, uh, this also depends on with what distance or to what distance have you pulled up the body. For example, if there is this one person and there is another person who are pulling the block of same mass, but one person pulled it by 10 centimeter only, and the another person actually pulled it to be to at several meters, maybe 4 meters, you will definitely say that if this person has pulled the object to a higher height, it means it has definitely put up more work into it. So it means work should directly be proportional to force as well as the displacement of the object. Now, in quantification, work is actually defined as F S cos theta. Now, why is this cos theta coming up? I'll tell you why. Let's say there is this object which is lying on a frictionless floor. All right. What you do is apply some force over it, and maybe a negligible force, very low force, and it is frictionless. Mu is equal to 0. But even in that case, it will accelerate, and after some time, it will gain considerable velocity as well, and it will cover displacements as well. What is happening over here is, see, by your very small application of force, let's say the gravity is acting here. So what is the work done due to gravity in this case? If you have your basic notion, then it should be mg into displacement. But it is not so, because whatever force you are applying on the object, this force was responsible for body to move along this line. This force is not at all responsible for the body to move along that line. So why should this force do some work if it is not responsible for the movement of the body? Only the forces which are responsible for movement of the body in that direction should have a say in the work done, which means uh, we should introduce some sort of angle, or we should introduce some sort of a term which is dependent on the angle, which means if they are perpendicular to each other, it means there should be no relation between the force and the work done, right? So that is why we have the cos theta term here, because let's say this is the force line and this is the displacement line. What you want to find out is what is the force, or what is the force which has actually done the work. What the way you can do this is, maybe find the component of the force in this direction, which will be, if this is theta, it will be cos theta. And when you have the component of the force in this direction, you can definitely go ahead and multiply it with the displacement it has covered along the same direction. Because if you are moving an object in a particular direction with the force, then it should move in the same direction as the displacement if there is no other force acting on it. So what is happening over here is, we have taken the component of the force which is parallel to the displacement, because as we have learned from this example, that only a parallel force can do a work, not any other force. Only a parallel force can do a work. So this will be f cos theta, which is the component of the force in this direction multiplied by s, and that is why we get the term fs cos theta. You can even write it in terms of f dot s. Dot is the dot product between two vectors. F and s are both vector quantities, right? And since you have work which is actually associated directly with the energy, which is a scalar quantity, so it must also have the units of the energy, which is joule. And since energy is a scalar quantity, work should also be a scalar quantity. And you have the resultant of two vectors multiplied with each other using a dot product is also a scalar quantity. That's why it is equal to work. Now uh, this is the joule, and in other manner, in kg meter per second, things like that. In the dimensional form, how can you write that? This is kg meter per second square multiplied by meter itself. So this is kg meter square per second square. This is the unit for work, which is nothing but joule. There was this scientist with the name Joule, which had done many contributions to the field of calorimetry. Actually, that's why we have given the term, the name of the scientist, which is Joule. So all forms of energy has the same SI in it, Joule, whether it is heat or anything else. Anyway, if you are clear with the work done, then we can even, let's say, there is this part of the track, and there is another part of the track. I have pushed the body with F1 force till here, and from here F2 force. What this basically means is the energy required to do that should be equal to the work done over the first path and the second path, which means work is additive in nature. The total work should be equal to work 1 plus work 2. And if you have a variable force, what you can do is integration, because integration is nothing but addition of very small components. So here what you can do is integration of the small work done should be equal to integration of f s cos theta from s1 displacement to s2 displacement, or s1 position to s2 position, and from s1 position to s2 position. So work done should be equal to um yes, what is that? Integration of, if f is constant it can come out, if f is not constant it can remain inside. So whatever I'll just leave it to this point, because if we don't know which one is going to be constant, if f is constant it will just come out, or otherwise if f is also variable it will remain inside the integral, and you will have to integrate in the same manner. So what portions have we covered till now? I think this we have covered, and this thing we have covered. These parts are yet to be. I think I forgot to give you this one, that there is this basic rule that energy can neither be created nor be destroyed. It's the same as the law of conservation of mass, which states that mass can neither be created nor be destroyed. Now, one can say that in nuclear reactions, mass does actually reduce or increases. It actually is not, because as per Einstein's theory of relativity, mass is almost the same as energy. They are just the different, maybe how you do how you do that 1 centimeter is equal to 10 millimeter. It's almost the same thing for mass and energy. That mass and energy are interchangeable. If you have some reduction in mass, the energy will get convert, or that reduction in mass will get converted into the um, energy, which is actually given by Einstein's theory of relativity, which has one of the results as the energy released is equal to delta m into c square, where c is the speed of light, speed of light, and delta m is the change of mass in the nuclear reaction. For example, if there is this atom of let's say maybe uranium 235, because it is more radioactive than the 238 isotope. So when it dissociates into the individual nuclei, which may have uh, mass which is smaller than 235, the net mass, maybe let's say that is 234, then you have a difference of uh, one proton, the mass of one proton. Since you have already the data on the mass of one proton, what you will do is the mass of the proton into c square. That will be the energy released from this reaction. So that is the example for calculation of energy released from a nuclear reaction. Anyway, it will not be of much use in this chapter, but you should know it, being a student of physics. Now, coming back to this part where I left you, kinetic energy. How do we calculate kinetic energy? First of all, kinetic energy, let's say there is this body on which some force is being applied, so that its energy or its velocity initially was zero, and after some displacement, the energy or the velocity becomes v. All right. Now what we can do is, can I say that the work done by this object, this force, should be equal to the gain in kinetic energy? Because whatever force this body has done, it has been converted into the motion of the body which has resulted into the kinetic energy of the body. And as per, as per the conservation of law of energy, or law of conservation of energy, we can say that if a body is gaining some energy, it must be getting that energy in the form of a work or another form of energy. So what we can do is, the work done while moving the object is equal to the kinetic energy, is equal to, we can write it in the format of f dot ds, right, f dot ds or fds, straightforward, because they are in the straight line. And yes, integral of this one, k is equal to integral of this one. Now how can you find f? That is simply mass into acceleration into ds. Mass is a constant in classical physics, that's why it comes out. And you have the integral of a. Now acceleration can also be written in two formats: dv divided by dt, as well as v dv by ds. I hope you know this. So I'll use this one here, v dv by ds, into this term, which is ds itself. Ds gets cancelled out, and since you have, let's say, u and v as the initial velocity, because we have got the variable dv here, so we should put the limits in that format itself, u to v. All right. So kinetic energy is equal to mass into, what's the integral of v dv? That is v square by 2, v square by 2, and the limit exists from u to v. This is the final velocity. So what we got from here is half comes out m into v square minus u square. This is the kinetic energy, change in kinetic energy of the body. Or if you want to find the kinetic energy at a fixed velocity, that will be simply half into mv square. This was change in kinetic energy, and this is the absolute form of kinetic energy. So kinetic energy, I guess, is clear here. Which one was that? Yes, kinetic energy. I think we can take it up later in the work energy theorem. Kinetic energy. And from, let's say, this thing, what about potential energy due to gravity? Due to gravity, what should that be? If you have an object of mass m, what is the minimum amount of force which must be applied to pull the object upwards? Let's say this is the zero position, 0, and you have to pull the object to a height h. Then what is the minimum amount of force with which we should pull the object? Of course it should be equal to mg. Only after countering the mg you will be able to pull the object upwards. So mg, it is the force with which you are working, or you are doing some work on the system. So should the change in potential energy due to the gravity, it should be equal to the work done by the person who is pulling the object? Of course it should be. So work done is nothing but f dot ds, or f dot s to be straightforward, and your force was mg, and the displacement was h in the upward direction. So this is simple, mg into h. So this is the potential energy due to gravity, which is equal to mgh. In the same fashion, if there is some difference in the height, let's say you are pulling at from h1 to h2, you can simply do h2 minus h1, and that will be the difference in potential energy. So that is the potential energy, yes, mgh. Now we will talk about the spring constant, spring force. How is it that some energy is also associated with the spring? Let's say there is this spring of spring constant k, and some let's say there is this mass m associated with it, and there's this wall. What you do is you apply some force on the system so that so that it slowly compresses. So F should be variable here, right? Because the more the body is compressed, let's say it is compressed by x distance, you will have to apply force is equal to kx here. So as to slightly pull the object or more, or compress the spring more. So what we have over here is integral of fs or fx, fdx. Because see, f why the reason I have put the whole thing inside integral is because f also is a variable here. The thing that we discussed here, I think, where was it? Yes, this one, this thing. So coming back to this thing, the spring one. So it should be from x1 position to x2 position, or let's say we take it from 0 to x. 0 to x, it means from this position to this position, which is x. It should be equal to, what's the force in spring system? What is the force with which you should push or compress the spring? It is always kx, where k is the spring constant, into dx integral over 0 to x. So what we got from here is k is a constant coming out, x ds integral x square by 2, 0 to x. So from here, potential energy associated with the spring is equal to half kx square. As simple as that. Alright. So that is the potential energy associated with the spring. Where is the spring? Yes, this one. And this is the work energy theorem. What this basically states that is, let's say you have an object on which multiple forces are acting on this, F1, F2, maybe F3 as well. So if you calculate the individual work done by all these forces, work due to 1 plus work due to 2 plus work due to 3, all these forces, there may be n number of forces, you will have to add the work done by each of the forces. If you add them up, what you'll get is the same as the change in kinetic energy of the body, delta ke. Why it will be so? Because we discussed earlier in the kinetic energy that you should be having some, or you should be able to do some work in order to impart some velocity into the object, and the velocity is the reason the object has some kinetic energy. That's why if you add all the work done by the system or by the forces acting on the system, you'll get the change in kinetic energy, nothing else. Now, this was the work energy theorem. Work energy theorem, which I think will be in the same format. Yes, this is the change in kinetic energy, right? Half into mv square minus half into mu square, which is nothing but half into m into v square minus u square, the same thing that we derived earlier. So this is also clear, I guess. Now, um, I think we did not discuss about the special cases for the work done. We can take them up because it's very simple. See, if you have a force, the way we defined, yeah, we can take it from here itself. The way we defined work done is equal to F dot S, right? So let's say you have an object on which some displacement can also only occur in the x direction. All right, let's say it is on the ground, and you can only have the displacement in the ground, towards the ground. And let's say you apply the force in the same direction. The cos theta component here will become 1. So it will be work is equal to Fs. But what if the force is not in this direction but in this direction, and the displacement is in this direction? Then you will have some theta over here, due to which it will be Fs cos theta, and if you have this angle ranging from 0 to 90 degree, you will have the cos theta value. This is the graph for cos theta. All these values from 0 to pi by 2 are positive, right? So it means fss fs into some positive term. Does it mean that f is a positive, sorry, work done is positive in case of theta in the range of 0 to pi by 2, right? In 0 to pi by 2, work done is positive. Let's say you have this force acting upwards or downwards, and the object is moving here, making an angle 90 degree. In that case, cos theta will be equal to 0 because cos 90 is equal to 0. So if f is perpendicular to displacement, then work done is equal to 0. This is the second case. This was the first case. Work done is positive only when the angle between the force and the displacement are less than 90 degree and greater than 0 degree. The third case could be that, let's say, there is this object which is continuously moving. Let's say it has some initial velocity, and I'm trying to apply some force over here, which is F, making an angle. See, if it initially has a velocity v, it will of course it will have to move to some distance in order to stop. It means during that motion, that is the displacement is still in the rightward direction, which means that if I say that this is the angle theta, then the the sorry, the work done by the force should be equal to f s cos theta, right? Now, since f and s are the magnitudes only, the cos theta for a obtuse angle, coming back to the graph of the this thing, see, this is the pi by 2 and this is the pi. So all this part is for the obtuse angle, right? And all of them are below the zero line, which means cos theta is a negative term when the angle is between 90 degree to 180 degree, which means work is negative if obtuse angle. Obtuse angle means pi by 2 to pi. So these were the three special cases which you can consider. This one was the first case, and the second case, and this is the third case. The same thing that we explained here. All right. So if all that is clear, I guess this is also fine. What we have over here is a very special case, and that is for a collision. I'll just explain it in the brief. How do you solve for collisions? Collision. First of all, what is a collision? Collision is nothing but interaction of two different bodies such that they impart impulse on each other. Impulse. Impulse is nothing but force multiplied by the short interval of time in which they are in contact. So, what this collision means is, let's say if this is, let's say I've considered this whole thing as a system, it means the collision here is an internal process, right? So, the forces must also be internal on each other, meaning that there is no external force acting on the system. And if there is no external force, can I say that momentum of the system should be conserved? Momentum should be conserved before and after the collision, right? Before and after the collision. All right. What it means is, let's say it has some velocity in this direction as u1, and this is mass m1, and this one has a mass m2 having some velocity u2. What this means is, and after the collision they gain a final velocity of v1, and maybe I can write it in this direction, and maybe a final velocity v2 in that direction. What I can write from law of conservation of momentum is only the only prerequisite for applying the momentum conservation is that F external should be equal to 0. Otherwise, it will not be applicable, the law of conservation of momentum. So, according to the law of conservation of momentum, m1 u1 plus m2 u2, which was the initial momentum of the system, should be equal to the final momentum of the system, which means m1 v1 plus m2 v2. This is the equation which will help you in solving for collision. Now, coming to a second type of equation that will also help you, because see, this is known and this is known. Of course, the masses are known, but this is a variable and this is also a variable. This is a single equation having two variables. It can't be solved, right? So you need another equation for this one. How can you find this another equation? By assuming two different cases. First one is energy is conserved. Energy is conserved. Why will the energy be conserved in the collision? Because let's say during the collision there was some deformity, which means these two balls were compressed with each other, and after some moment they released each other, meaning that whatever potential energy went into compressing these two objects was released later in the form of kinetic energy, which means energy should be conserved here. So if you have to conserve energy, what was the initial kinetic energy for the system? It should be equal to half m1 u1 square plus half m2 u2 square. This one should be the initial energy, and since I said that energy is conserved should be equal to this final kinetic energy, half m v1 square m1 v1 square plus half m2 v2 square. Now what you have over here is all the known things are here, because initial velocity was also given and the mass is also given. The problem was these two variables have only one equation, had only one equation earlier. Now you have another equation relating these two variables. So two variables and two equations. This can be easily solved, right? So you can solve in this manner. The another case could be, this is called elastic collision. Elastic collision. The second example could be of inelastic collision. Inelastic collision. From the term itself, you must have understood that energy is not going to conserved in this system. Or I can write it as mechanical energy is not conserved, because energy should also always be conserved. That is the basic law of conservation of energy. But mechanical energy is not conserved here. Conserved. Then where did it go? Actually, in these cases, inelastic cases, when the collision happens, they compress each other, but while returning back, the compression is not actually fully resolved after they leave each other. The deformity in the object remains as such. So it means mechanical energy is not conserved. Where is that energy going? It is going into the deformation of the body. In that deformation, the energy is being lost. All right. But in this case, what you can do is, since there is this elastic collision and there is this inelastic collision, the extreme case for inelastic collision is completely inelastic collision. Completely inelastic collision. What it means is they will actually never leave each other, and they will actually form a combined entity. Two different masses combining each other, fusing into each other. In that case, of course, it will have a constant velocity, right? V for the whole thing. So what I can do is again apply the momentum conservation, which was m1 u1 plus m2 u2 should be equal to, what is the net mass of the system which has stuck into each other? That should be m1 plus m2 into a final velocity which is v. There is no scope for v1 and v2 because they are going to stick to each other. All right. If that is clear, this is the completely inelastic case, this is the completely elastic case, but real life situations are always partially inelastic, partially inelastic. All right. Coming back to the mind map, I think we have discussed perfectly elastic collision and perfectly inelastic collision. Now there's this only thing that is left out till now, or maybe we can take up one more topic which is not mentioned here, is head on and oblique collision. All right. Head on and oblique collision. Just a second. I think my battery is going down. I'll just yes. So oblique and slash head on collision. If there are two balls which are colliding each other perfectly straight, we generally call it head on collision. They're colliding head on. But what is actually happening over here is, as I told you, that there is always transfer of impulse in the collision. Let's say this is the center of mass of this body and this is the center of mass of this body. Then this is the line of the transfer of impulse. If the point of contact, if the point of contact matches with the or initial velocity, what was the direction of the velocity? It was this one and this one, right? Both of them parallel to the line of collision or the line of transfer of impulse. In this case, it is called head-on collision, but there could be another case in which there is this collision. The velocity was in this direction and in this direction, but since the transfer of impulse is always in the direction of the line joining the center of masses, are these parallel to each other? Of course not. This type of situation is called oblique collision. Whatever we talked about in the initial part was about head-on collision. Whatever we talked about in the conservation of momentum in the collision, that was about the head-on collision. But oblique collision is not so difficult actually. What you have to do is, see, this whole principle of conservation of momentum was along the line of transfer of impulse. So what you can do is, if this is the object having velocity in this direction and this is the line of impulse, what you need to do is take the component of the velocity in this direction and the other component should be in this direction, right? So this is the one component v1 and v2 and this is the v net. You can apply all the laws of conservation of momentum and all the things on this component, because this is the component which is going to get changed due to the transfer of impulse. Transfer of impulse is in this direction. It cannot change the velocity which is in this direction perpendicular to each, right? So the only velocity which it can change is the velocity which is in the line of impulse or line in of transfer of impulse. So always, let's say there is this second ball having some velocity here. You just take the component of the velocity in this direction and this direction. This component and this component you can just use as in this situation. You can just apply all the equation of motion laws of conservation of momentum, and after that whatever you are left with, you can actually just add it up. Because why you can add it up? Let's say this was 20 meter per second and after the collision it came out to be 10 meter per second. What you just have to do is just plug the value of v2. It should be remaining perpendicular to each other, so the final value of the velocity should be equal to 10 square plus v2 square. V2 is the same velocity which it initially had in in this direction. The original velocity was in is sorry, original velocity was in the horizontal direction, yes, but since the line of transfer of impulse is not actually horizontal, you just had to take divide the velocity into two components. This component got changed due to the collision, this component will not get changed. So whatever value of the velocity in the line of impulse you got in the final value, you just have to add this value as well. And since they are perpendicular to each other, they will not just be added straight, and they will be added in this format: a square plus b square the whole under root. I hope that is clear. Oblique and head on collision. Now this is also clear. Plus head on slash oblique collision. This one is done. Now I think this is the only part that is left till now. So coming to this is the work, relating to the change in work. For example, there is this maybe I can use on the, or let's just use on this pen itself. Let's say you're applying a force F which is constant. Okay, now this body will have some acceleration, and with time, let's say t1, how you can find the distance covered or the displacement of the body? S is equal to ut plus half a t square. Since u is equal to 0 here, that will be half a t square, right? It means the displacement is not directly proportional to the time. It is actually proportional to the time square, which means that even if you apply a constant force, you will not get a constant supply of energy. You will actually need to apply more and more energy. But why? Because uh, whatever force that you had applied or whatever work you were doing, that was going into, sorry, the work was going into the kinetic energy. And if the velocity of the object, sorry, the displacement of the object is continuously increasing, but it is not increasing in the format of t but t square, it means for the work done, the work done can also change, right, with time. That was the whole reason I took this example, to give you the feel that work done can be changing variable. Let's say from 0 to 1 second, the work done was 1 joule. From 1 to 2 second, the work done was 2 joule. From 2 to 3 second, there can be maybe 4 joule. So the work done per unit time is changing with each other situation. There must be some variable to take into account of that thing, that change, right? So that is the thing, that is power. Power is defined as rate of change of work, of change of work. What is meaning of rate of change of any quantity? Which means rate of change of the rate of change of work with respect to time. Rate of change means in particular time difference delta t, what is the difference in the quantity which is work actually here. So what is the difference in work done by the object in the particular time frame? That will be the power given by the source. Since I can also write it in this format, delta w by delta t, if it is something scary to some of the students. Now what should be the SI unit of this one? This one has a unit of joule, and this is having a unit of time, second. So power should have the SI unit of joules per second. Actually we have a special name for it, which is called watt. It is named after the James Watt, famous inventor. And if you have to write the dimensions, what was the dimension of joule? Fs. So kg meter square per second square multiplied by, sorry, divided by time, right? So the dimension for power actually comes out to be kg meter square per second cube. This is the dimension of power, which is having the SI unit of watt. There can be other units of power as well. For example, horsepower. I think it was 746 watts. Is it the same value I'm talking about? Yes. 1 horsepower. Actually, horsepower is not generally used in our problems, but it is mostly used in the power which a car can generate. It has been traditionally been expressed in the form of horsepower. That's why you still have the term horsepower around, but it is generally used in mechanical uh, engines, to find the power of mechanical engines. Now, there is this term 1 kilowatt hour. First of all, kilowatt is the unit for energy, sorry, uh, power, and H is the unit for time, which means if you have an engine which is doing a work of 1 kilowatt and it has done work continuously for 1 hour, what is the net amount of energy which it has imparted into the system? We can simply do this because since power is equal to work done by time taken, work done can easily be calculated as power into delta t. Since power is the same as 1 kilowatt, in this case work is equal to 1 kilowatt means 1000 watts. I've converted this into SI unit, which is watt, and 1 hour. But 1 hour is not a SI unit, right? You have to convert it in the form of seconds. So that is 60 minutes, and if you multiply by 60 further, that will be in the form of seconds. So this is nothing but 10 to the power 3, 1, 2. So 36 into 10 to the power 5 joules, which is the same as 3.6 into 10 to the power 6 joules. So that is the equivalent of 1 kilowatt hour. I hope this mind map was clear to you. This one is also covered. And thank you. That is all.